In this video, we're going to look at resolution of vectors. That is, if you take one vector, one force vector, you can resolve it into component forces. This is typically done with muscles to determine what forces these muscles are actually exerting on a system of levers. So in this case, we'll just draw a humerus bone, okay, and then here we have the ulna. Alright. Although you can just kind of consider this to be the forearm if we don't want to get too technical. Alright. Then from here we have, let's just say this is the long head of the biceps. Alright. And here's the biceps muscle. Alright. Biceps muscle, and it's going to insert down here on the forearm, right? Actually on the radius. So that muscle generates a force, okay, and that force can be represented by, let's say, this vector. I'll try to make it extra thick so we can kind of see it. This vector here. Alright, so here's the point of application of force. Here the magnitude of the force is represented by the length of the vector, and the direction and sense of the force are represented by the shaft and the arrow. Okay? But when you have that vector, okay, so here we have a vector of force. So just looking at the force vector here, the direction that it goes, you would think that going in this direction, this whole bone is just going to slide in that direction, right? That's what the vector is doing. It's just pulling the whole thing in that direction. But we all know that's not what happens. The reason that's not what happens is you have an axis over here that constrains this motion of this lever. So, let's see what actually happens. Well, in order to determine what actually happens, you need to look at a couple of things. This vector can be resolved into two component vectors. One of the component vectors always goes through the axis of joint motion. I think in Newman it talks about the one component of the vector always going through the long axis of the bone. And that's true, but I think it's more helpful to say it always goes through the axis of joint motion, because sometimes we're dealing with bones that aren't all that long, and then it can get a little confusing. So here we have this here, and at this point I'm going to actually, just for the sake of illustration, bring this down just a little bit farther, just so we can kind of see this. In the so-called perfect world of physics, all this would be just represented by lines and points, not necessarily a diagram of an actual, the actual anatomy. Anyway, so this vector, which is the resultant vector, we're going to actually resolve into its component forces. So one of those component forces goes from here and goes straight through that axis of joint motion. Okay, so that's one of the parts of that force. Then the other component goes perpendicular to that first one, always perpendicular. Okay, so that one you just start here and you go perpendicular. Okay, and you can draw them as long as you want. We're going to actually figure out what the length is in a minute. But these are the two components of this force. The way you figure out the actual length of these component vectors in order to in order to determine what their relative forces are is the parallelogram method, and it's kind of a parallelogram in reverse, because we know our resultant. We just have to figure out what the length is of the these two sides of our parallelogram. So, from each of these sides, we're going to draw the other half of the parallelogram. And the way we draw it is, it's always going to be, again, perpendicular or perpendicular to this line or parallel to the other vector here. And you're going to draw it as long, to a certain length, and that length is going to be up into this right here. That is your actual muscle force vector. Okay, so, and I'm going to draw it as a dotted line here. If my thing isn't working very good, I'll use black instead. Alright, I'm going to draw this as a dotted line. Alright, right on down. So I'm going parallel. I'll get out of your way in a minute so you can see. Parallel to this line from this line. So that is the actual length then. And I'll get rid of the rest. That's the actual length of this force vector. So I can draw my arrow now that I know where it goes. I can draw my arrow right there. Okay? For this other vector, again, I'm going to start from the tip of my muscle force vector, and I'm just going to go perpendicular to this vector or parallel to the other one. There, that means the same thing since we drew the two component vectors perpendicular to each other. And that tells me the length of this other vector. So I'll just erase the leftover there and draw my arrow there. Alright? So this first vector here, and maybe I'll erase the actual kind of anatomical drawing a little bit to help you see it. Okay. So my first vector here, representing the force of that long head of the biceps muscle in red, can then be resolved into its two component vectors by starting at the point of application, alright, or point of insertion, drawing one that goes through the axis of joint motion, drawing another that goes perpendicular to that first one, using this muscle force vector to, through the parallelogram method, determine the relative length of these two, and then you have the component vectors. So, what do these component vectors actually mean then? That's the big question. Well, what they mean is this. Each muscle force can be, or has two effects, okay? One effect of the muscle force is actual rotational motion. That is, you get movement of the limb about an axis, okay? You create rotation as this forearm rotates around the axis at the elbow joint, or at the humeral ulnar joint. That's one product of this muscle force, but there's another product of that muscle force as well, and that is that you actually get either joint compression or joint distraction. So the joint either gets loaded or unloaded as a result of this muscle force. In this case, we have this vector down here that indicates that we have a small amount of joint loading at the humeral ulnar joint as a result of the biceps contracting in this particular position. We also have a relatively much larger amount of rotation, also known as elbow flexion. So those are the two components of that muscle force that exist from that force of that long head of the biceps. One that creates either joint loading or joint unloading, that is joint compression or joint distraction, and one that creates some sort of rotation. If you play around with this for a little while and put this forearm in different positions, you'll notice when you make your parallelograms that those relative length of those two components of that muscle force change dramatically. So that might be a good active learning and thinking exercise, is to do this same thing, but do it with, let's say, the elbow completely extended, completely straight. Maybe do it with the elbow almost completely flexed. See what difference that makes in the relative length and direction, for that matter, of the two components of that muscle force's action.